Hello, welcome to the presentation of the paper Contour-based intracoding using Gaussian processes and neural networks. My name is Laude and I wrote this paper while I was with Leibniz University, Hanover. When I started the research for this project, I thought about the limitations of the conventional intracoding as it is used in HEVC. Here, given a reference area, boundary samples, which are called reference samples, are continued into the block to be coded, here depicted in green. The limitations are known, and they are, for instance, that per block only one direction can be used to extrapolate the boundary samples. Only a linear extrapolation is possible for the directional modes, and also the used samples in the reference area are limited by one pell width or height. To cope with these limitations, I proposed a couple of prior works on which, given an input, a two-stage process was performed to determine the predicted output. The first step was a contour extrapolation, where contours were detected in the reference area, extrapolated with different means. Then sample values were predicted given the contours, given the reference area, also with different means, to finally form the prediction for the currently coded block. For this paper, I propose two methods for improving intra-prediction. The first contribution is a stochastic model for contour extrapolation, and the second contribution is a sample value prediction algorithm using neural networks. The first contribution replaces all contour models from the prior work, and the second contribution replaces the sample value predictors also from prior works. With these algorithms, I increase the coding efficiency of HEVC by up to 5%. I start by detecting all contours in the reference area. In the image on the left, green is the block to be coded, and there are two contours which are detected using the Kenny method. Contours which do not hit the block to be coded are omitted. As a result of the Kenny method, and after some processing afterwards, I have for each contour two vectors. One vector with all the x values of the contour and another vector with all the y values of the contour. Given the x vector and the y vector of the detected contours, the observation of the process to be modeled, in this case the ground truth of the detected contour, is formulated as B, which contains the x and the y values. This process is to be modeled using a noise-prone Gaussian process, which is formulated here, where we have the Gaussian process on the right, and we have the observation of the model, which is called B tilde, which contains x. These x values are identical to these x values, and f. F are the values of the modeled contour. In the Gaussian process, we have a mean value, a covariance function, and noise. Let's take a closer look at this covariance function. A squared exponential function is used here. Its formulation is on the slide at the left. This function is differentiable unlimited times, which in consequence leads to smooth extrapolations of the contours. This is what is expected for the contours in the signal to be coded, especially given the partitioning schemes in modern video codecs, which can partition the image in different sized regions, which can follow contours in the image. So it is not expected that contours which are not smooth are found very often here. This covariance function has two hyperparameters, theta and c. These parameters are, for now, undetermined. This is called the prior Gaussian process. later on, they will be determined for each contour. This is also called the training of the Gaussian process. This posterior Gaussian process, which is specific for a given contour, starts by these hyperparameters, and then the goal is to maximize the correspondence of the Gaussian process observations f with the actual values y of the contour pixels. For this purpose, the marginal likelihood is formulated and a Newton method is applied to optimize this problem. In consequence, the hyperparameters which maximize the correspondence are determined. They are annotated using max, and then these hyperparameters are put back into the formulation of the Gaussian process, and then extrapolations can be performed. For this extrapolation, we start by formulating a multivariate Gaussian distribution. This is in this equation. Here we have x, the detected points, which are given. These are the x values of the contour in the reference area. We also do know y, which are the observations for the detected points. They are also given in the reference area. Then we do have x asterisks, which are the x values of the contour to be extrapolated. We determine these by simply iterating through the x values of the block to be coded. We also do have f asterisks here, which are the observations of the posterior Gaussian process for the extrapolated contours. These values are unknown. So the goal here is to find a formulation which gives us f asterisks given x asterisks, and given y. So given all the values we do have. The solution for this problem can be found by using a math textbook and results in this formulation at the bottom. Here we do have f asterisks given the three sets of known values as a Gaussian process output here, where the first half of the formulation represents f asterisks. So these are the y values of the extrapolated contour, and they depend on the known x values, the x values of the contour to be extrapolated, and the known y values. The second half of the expression represents the confidence in the prediction, which will also be used for the sample value prediction, which I will present later on. Let's move on to the second contribution of this paper, the neural network-based sample value prediction. As training data, we use images from the RACE database. A few examples of this database are depicted on the left side. These images are uncompressed, meaning that no compression artifacts are inherent in these images, which makes them suitable for prediction purposes in the context of coding images and videos. The resolution of these images is between 3000 times 2000 and roughly 5000 times 3200, and the content is various. The authors of the database divide the content into 8 different categories. For instance, on the left side you can see buildings, landscapes, etc. As network architecture, we use an autoencoder. For the details of the architecture, I need to refer to the manuscript given the amount of time for the presentation. The network has 4 different inputs, as shown on the left side. We have the samples of the reference area. We have the result of the contour modeling described in the previous contribution of this paper. We also have the confidence of the contour modeling. And we have a map indicating the availability of reference samples, which can differ depending on where we are inside an image or how the partitioning scheme is. The autoencoder processes these inputs
to derive the output, the sample value prediction, which is the sample values of the predicted block. As cost function for training the network, we use the SATD, sum of absolute transform differences, which is also known as cost function for video coding algorithms. For the rationale behind this, we are assuming that the coefficients, denoted as C, are roughly Laplacian distributed, which can be modeled as in this equation. Then we can approximate the rate for an individual coefficient as the information content, which is formulated as this, in essence proportional to a constant multiplied by the absolute value of the coefficient. And if we consider not only the rate for an individual coefficient, but for all of them, we can formulate that the entropy of these coefficients is proportional to the sum of the absolute transform differences. Hence, this is a suitable cost function. For the experimental setup, we use common test conditions as defined for HEVC, and we implement the proposed methods as an additional coding mode in HM. The anchor is HM without the proposed methods. In addition to the common test condition experiments, we perform some supplemental experiments to gain further insights. For instance, we use additional test sequences, the texture-based sequences proposed by Bristol University, and also some user-generated content. Also, we assess the performance on lower bit rates. Before I go into numeric results, I would like to show some exemplary predicted signals. In the top row, we see the original signal, and in the bottom row, we see corresponding predicted signals with the currently coded block being within the red area. In the two middle examples, we see that the prediction works quite well. In the left image, we see the limitations of the algorithms, namely these darker areas, which are unpredictable from the reference area, are not in the predicted signal as expected. In the right image, we see that these different directions of the bars are also continued correctly. We can also see that the predictions get blurrier to the bottom right of the currently coded block as the confidence for these areas is lower. On this slide, the BD rates for the conducted experiments are summarized for the three categories: all intra, random access, and low delay. Also, the results for high bit rates and low bit rates are reported separately. One can observe that for high bit rates and all intra, 0.5% BD rate is gained, and for low bit rates, roughly 1%. When one takes a look at individual sequences, coding gains up to 3.4% for all intra and up to 5% for other configurations are achieved. One can also observe that the coding gains are higher for high resolution content and for user-generated content, whereas for low resolution content and for screen content, the results are lower. This reflects the availability of this content in the training data. We also studied the mode usage, meaning the percentage of pixels which is coded using the proposed methods. Also, in the same table scheme as on the previous slides, we see that between 13 and 18% of the pixels is coded using our method for all intra, with the results being lower for the configurations which allow motion compensated predictions. The remaining pixels are either predicted by HEVC intra, in the case of all intra coding, or by HEVC intra or HEVC inter for the other two configurations. With that being said, I would like to summarize this presentation. We propose two methods for improving intra prediction. The first contribution of this paper is the stochastic contour model for extrapolating contours. The second contribution is a sample value prediction using neural networks. In summary, we increased the HEVC coding efficiency by up to 5%. Thank you for your attention.